In this video, we are looking at Introduction to Polynomial Functions. Specifically today, we'll be using the leading term test to determine the shape of a polynomial. We'll also be trying to determine the zeros of polynomials by group factoring, or if they're already factored, determine what the zeros are, and something called multiplicities. And lastly, we'll just look at one applied problem with polynomials. Now, before I get going with the video, I have to explain the picture. That's my bike there. And this path that is there is something called violet tendencies. One of my favorite descents in Lethbridge. If you want to go on a nice walk or hike or bike, well, it's a little dangerous biking, but if you want to go on one, look for violet tendencies. Okay, so polynomial functions, we've already looked at a couple of them. One of them was linear functions. So y equals 2x plus 1, y equals 2x squared plus 3x minus 1 would be a quadratic function. And then today we'll look at cubic functions and quartic functions and any of the ones beyond that. Maybe just take a second in Desmos to graph all three of those and just to take a look at the shapes of their graphs. Okay, so I did those, and there that first graph, 2x plus 1, is a straight line, linear function. Let me hide that one and show the next one. That's a quadratic function. And we, in the last few sections, looked at how to determine what the x-intercepts were, or what the vertex was for a quadratic function. So today we're extending our discussion of polynomial functions to cubics and quartics and beyond. Notice that this one, it almost looks like two parabolas connected. But again, with these, what we're going to be looking at in this section and the next section is where they cross the x-axis. So I'll be looking for that point, and that point. And probably I could look at intermediate vertices as well, but we're going to focus just on those x-intercepts. So what I'd like you to do is just take a look at these, and if you wanted to graph some of these in Desmos or graphing calculator, you could. But I'd like you to look at these equations. Oops. Look at these equations here, and these ones down here, and take a look at the graph below. I'm just going to give you a minute or so just to look at them and look for similarities, look for differences, and make some kind of observation or some kind of rule that you can go with to say, if I see a polynomial that looks like this, then I know that the graph is going to look like that. Okay, I'm just going to give you, well, maybe pause and look at those and see if you can do that. Okay, hopefully you've taken a look at them. You'll notice that these ones are all odd degrees, and these are all the leading terms, and so that would be the degree of the polynomial. All of these are odd degrees. The ones down at the bottom are also odd, but notice that they have a minus sign in front. All of them have a minus sign. Hopefully you've observed that. Now, in taking a look at these positive odd up top, notice that they all start at the bottom. All of them start at the bottom, and they go up and do their thing, and they all end going up. So I like to say for these ones that if I have an odd degree and that leading term is positive, then I'm going to have a graph that does this kind of thing. Okay, so it starts low and it ends high. Okay, looking down at the bottom ones here, they're also odd, but these ones are minus, and notice it's its opposite. So the starting, they start, and I'm always starting going left to right. So I'm starting up here, they start coming down, so they start high, and they end up going low. Start high, end low. Start high, end low. And that's common of all of them. So if I have an odd negative graph, it starts high, it does its thing, and then goes down. So it starts high, goes low. One other thing to note about these, and maybe you notice them, is that the degree up here dictates the maximum number of x-intercepts or zeros that that graph would have. So this one's a cubic, and so there's 1, 2, 3 x-intercepts. This one's is a 5 quintic. Don't know what the name would be. Anyway, 1, 2, 3, 4, 5. So the degree indicates the possible x-intercepts. Let me write that too. Degree indicates the possible, maybe not possible, maybe maximum is a better word there. Maximum number of x-intercepts. The other thing maybe that you notice, and there could be lots of other things that I didn't notice, but the other thing is number of turning points. So when you look, let's do this x to the 7th graph. There's a turning point, there's a turning point, there's one, there's one, there's one, there's one. So if you count those, there's 6 turning points. And the number of turning points is always one less than what the degree is. So if you get the degree of the polynomial and you subtract 1, that gives you the number of turning points. Okay, that's good. Now let's take a look at even degree and do the same thing with even degree. Okay, you might want to press pause and just look and see if the same things apply. Okay, hopefully you have pressed play again. So if I have an even polynomial and it's positive, all these ones up here are positive, where does it start and where does it end? These ones always start high and they end going in the same direction. If I have an even number, so here, even, if my degree is even, if it's negative, then they all start low and end low. Start low, end low, start low, end low, start low, end low. In terms of maximum number of x-intercepts, so the x-intercepts are always whatever the degree is. So if the degree is 2, I'm going to have 2 x-intercepts. X-intercepts you get just from the degree, just like in the last one. And then the other thing is the turning points. See if the same thing applies. So if I have a degree 2, 1 turning point. Degree 4, there should be 4 or 3 turning points. 1, 2, 3. Okay, so the number of turning points is whatever the degree is, minus 1. Okay, let's have a quick little quiz. So what I'd like you to do is just draw what you think those graphs will look like. Press pause, draw what you think based on your observations on the last 2 slides, and then press play and see if you're right. So this one here, the degree is 5, so it's odd. The sign in front of it is positive, so it's an odd positive. So it's going to start low and end high. So it'll look something like this. Something will happen in here and it'll go up. If you want, you can also say there's 5 possible zeros or x-intercepts, and there's 4 turning points. Next one, this one is even, but it's negative. So it's going to start low and end low. So it'll look something like that. Again, there will be 4 zeros and 3 turning points. Last one, well, that's a good one. So this is an odd and it's negative. So it's going to start high and end low. So start up here somewhere, do funky things and end up going that way. 39 possible zeros and 38 turning points. Okay, hopefully you got the idea from that. Now let's focus in on what the zeros of the polynomials will be, or in other words, what the x-intercepts are. So here's a polynomial, f of x equals minus 2x, x plus 1, x minus 3, where they factored out the polynomial. And if I want to know what the zeros are, what we've always done is replace f of x with 0, minus x plus 1, x minus 3. And now we solve that equation. To do that, we've got three things multiplied together to give me 0. One of them has to be 0. So either minus 2x is equal to 0, or x plus 1 is equal to 0, or x minus 3 is equal to 0. So in the first one, dividing both sides by minus 2, you get x is equal to 0. This one's subtracting 1 from both sides, adding 3 to both sides. So my zeros for this, and it was nice that it was factored already, are 0, minus 1, and 3. Let's just take a look graphically at what that looks like. Okay, so there I've graphed it. Let me just make it a little bit bigger. There we go. Okay, so just take a look and see where it crosses the x-axis. Sure enough, it looks like it crosses at 0 and at -1 and +3. Notice it also obeys those rules that we talked about, where this one, there are 3 factors, so this would be an x cubed graph. There's a minus out front, so it's minus. So whatever rules we had for an odd negative should apply. And we said odd negatives start high and end low. And they have a possibility of 3 x-intercepts, and there they are. Okay, here's another one to try. This one, unfortunately, isn't factored, but I'm hoping that I can factor this fairly easily. So I'm trying to find the zeros. What I'm going to try is group factoring. So I'm going to factor an x squared out of this. That'll leave me with x minus 4. Out of this part, I'm going to factor out a -4, and that'll leave me with a positive x, and 16 divided -4 is a -4. Okay, this is equal to f of x. Then, since the x minus 4s are common, I can pull an x minus 4 out, and I'll be left with x squared minus 4. Oh, and then I can factor that too. So it'll be x minus 4, and this is the difference of squares. So x minus 2, x plus 2. So notice I have 3, my degree is 3, and I wind up with 3 factors. From those factors, I'll get 3 zeros. So x equals 4, x equals 2, and x equals a minus 2 when I equate that to 0. So in my graph, since it's cubic and positive, it should start low and end high. And it should cross the graph at those points. Go ahead and graph yours on decimals. I'll do the same and see if we get what we're supposed to. Okay, so here's what I got. And it looks like it crosses at the spots where I wanted it to, at 2 or -2, +2, and +4. And it has the low to high kind of shape on it. We're good. Why don't you try one? Go ahead and try it. Press pause, try it, graph it on decimals, and then come back to see if you are right. Okay, I'm going to group factor again. So x squared, x minus 2, and then take out a -1, so it'll be x minus 2. The x minus 2's match, so I can factor the x minus 2 out, left with x squared minus 1. Oh, that's a difference of squares like the last one. So it'll be x minus 1, x plus 1. So if I equate that to 0 and solve, I'll get x being equal to 2, 1, and minus 1. And now let me graph that and see if we have the right kind of shape. This is positive. It should go like that. There we go. So you can see it has the low to high shape to it. It crosses graph at -1, +1, and +2. Good. Now, with some polynomials, we have something funny that happens, and it's called multiplicity. And it's when you have the same 0 occur a couple of times. For example, in this one here. So here, I've got a polynomial. There are 3 factors. There's 1 here, and then there's 2 of them here. So there's a total of 3 factors. So the degree will be 3. So, and since it's positive, it's going to look like this. But because there's 2 x-intercepts or 2 zeros that are the same, something funny happens in the graph. And this is what happens. When you have a multiplicity here, let me figure out the zeros first, and then we'll talk about that. So to figure out the zeros, I'm just going to write both of those out. You set it equal to 0, so this one will be x equals a minus 2, this will be x equals a positive 2, and this will be x equals positive 2. Because these are the same, we would say we have a 0 of minus 2, and we have another 0 of 2 with a multiplicity of however many repeated. So there's 2 of them. So we have a 0 of 2 with a multiplicity of 2. Graphically, what happens is quite interesting with that, is that it has to do something on the graph at that point. But what it does is, I guess, a little surprising. Let me show you. So I have one right there. That's one of these zeros. And then I have one right here, but there's 2 of them. I've never seen this in a book, but what I do is if there's 2 of them, I put a circle around there just to indicate that something funny is happening. Since this is a cubic, it has to have this shape to it. So the graph's going to come up like this, and the x-intercept I'm not going to worry about for now. But then when it comes down, rather than go through at this point, it just comes down and touches and bounces the other way. So when you have a multiplicity that's even, like this, it just comes down and touches. Let me show you what happens when you have a multiplicity that's odd, like this one. So it's similar kind of graph. Let's set it equal to 0. And so I have x plus 2, and then I've got 3 of these this time. So I have negative 2 is one of the x-intercepts. Positive 2, since there's 3 of them, I'll say it's positive 2 with multiplicity of 3. Now, since there are 4 zeros, or 4 factors, or your degree is 4, and it's positive, that's one of those high to high graphs, so something like that. Okay, so let's try and impose this shape on those x-intercepts. So I have minus 2, something happens, and minus 3, something happens. I guess there's 3 things. I could put another circle. Never done that before. Anyway, that just indicates that there's a multiplicity of 3. So the graph has to come down like this. And now when it comes up to this one, since there's an odd multiplicity, what it does is it does a bend through that point. So it comes up and does sort of a bend and goes through. And that's what that graph would look like. So that's an odd multiplicity. Okay, why don't you try one? Here's one function. And if you want, you can use decimals to graph that and just confirm with decimals what you think is happening. So press pause, try it, and then come back. So here, my zeros will be 1, and it has a multiplicity of 2. And then I have x equals minus 1, and x is equal to 3. So at 1, there's something that happens. Oh, multiplicity of 2, let me put a circle around it. Minus 1, it crosses, and at a positive 3, it crosses. Again, if I count up the factors, there's 1, 2, 3, 4 factors. So this is a quartic graph. It's minus at the front there, meaning it's going to start low and end low. It'll have something like that. So I want to do this shape. Notice what if it has a multiplicity of 2, it's going to do a bounce at that point. So my graph is going to come up like this, come back down, and it's going to do a bounce at that point, come back up somewhere, and then come back through. I'm not too worried right now about how high up things go, just as long as you have the shape. Okay, the last question for this section is sort of an applied one. I'm going to try to do a bunch of things with this question. It's the old make a box out of a piece of paper question. Let's say we've got a piece of paper and I want to make a box out of it. Let's say the piece of paper is 12 by 8. And I want to make a box. And it's fairly easy to make a box because all you have to do is cut a corner out of this. Well, cut a corner out of all the corners. So cut a corner out of all of those. And then when you fold the sides up, you make a box. You have to do some tape and whatever. Now, if I want to know what the volume of the box is, and maybe I want to maximize that volume. Well, let's not worry about maximizing now, but maybe I want to determine what that volume is, depending on how big a corner I cut out. So let's first just suppose that well, we don't know what the number is. Let's call that x. So that corner that we're cutting out is a square, and it's x by x. And this corner is also x by x. All of them are x by x. So if I wanted to know what the volume of a box is, I know it's length times width times height. So my box is going to wind up being this, right? Because I fold the sides up. So the bottom of my box will look like that. So I need to know the distance from here to there. And that'll be the whole 8 distance. Take away these two x's. So it'll be 8 minus 2x. So that'll be my width of my box. And then the length of my box will be from here to there. And that's going to be 12, the whole distance minus the 2x's. So 12 minus 2x. And then the height of the box, because I'm folding these corners in, the height of the box is just going to be x. Okay, so if I take that and plug this in, the length is 12 minus 2x, and the width is 8 minus 2x, and the height is just plain x. There I get an equation or a polynomial that describes the volume of a box, and based on x. So I could make x 3, or I could make it 1, or 0.5. I can make any size box I want, and this polynomial will tell me. Now, let's, I guess we could multiply all that out, but rather than multiply it all out, what I want you to do is, and I'll do it too, is plug that into decimals and see what kind of shape you get. I'll do it too. Okay, I finished mine, and I had to squeeze it up and shrink and expand it a little bit to get the thing looking like it is. Notice since there's three factors, that it's a cubic, and so it starts from low and ends high. Now this information down here doesn't make any sense because x refers to a distance in that I'm cutting off of the box in the corner there. So the polynomial that I'm going to be worried about, probably from here, probably I would stop there because I won't have a negative distance either. But this part of the polynomial in between there, that interval, describes what happens with the volume of the box based on how big a chunk you take out of the corner. So as you go up, as you increase that x, the chunk that you're taking out, the volume of that box increases until you get to a point right there. And that point looks to be about 1.5-ish, something like that. And at 1.5, the volume of that box will be the largest. So you can put the most amount of stuff in that box. As soon as you go past that, the volume decreases until you get to be about 4. Almost at about 4 is when, and I guess that makes sense, you wouldn't have a box at all. Now let's just see what those volumes would be at those 2 points. Oops. So at 1.5 and 4. So I can take my volume of the box, volume is equal to 12 minus 2x times 8 minus 2x. And like I said, you could have multiplied that all out if you wanted to. But let's plug in 1.5 for x to see what the volume of that box will be. And here you might need to use your calculator. So it'll be 12 minus 2 times 1.5. And then 8 minus 2 times 1.5 times 1.5. Just do that on your calculator, see what you come up with. Be, I think, 9. That'd be 5 times 1.5. So it'd be 45 times 1.5. 22, so it'd be 67. I think it should come out to about 67.5. So that would be the volume of the box that you could make if the chunk that you cut out is 1.5 inches. If you wanted to try 4, you could do that too. But notice when you put a 4 in, specifically, let me get a different color here. Specifically, if you put a 4 in right there, 2 times 4 is 8, and then 8 take away 8 is 0, and 0 times anything is going to be 0. Basically, you won't have any box at all when you get to 4. Anyway, that's an example of a polynomial function that gives us a graph or gives us an idea of what happens to the volume of a box based on some kind of variable. There's lots of other questions in your homework that are similar to that, and typically what they do is they don't make you come up with the polynomial. They give you the polynomial, and then they ask some questions about it. In this video, we have looked at using the leading term test to determine the shape of a graph. We've also found zeros and multiplicity of those zeros. And then lastly, we just looked at a quick model.